In this presentation, I will talk about positioning in highly dynamic industrial environments, and also I will talk about how we can provide accurate location services using cross-modality training. Location technologies are quite important nowadays, mainly because they are the key requirement for many applications, such as navigation in hospitals, location-based trigger information in museums, location-based advertising in shopping centers, and many more. So over the last years, location technologies have reached a significant level of maturity. For instance, we know how to efficiently do simultaneous localization and mapping using GraphSlam. We also have systems like MacLoc, Mapcraft, RAVEL, and Optimus that use techniques such as map matching, visual tracking, and sensor fusion to provide accurate positioning services, especially in indoor environments. So indoor positioning systems make certain assumptions. Specifically, they assume environmental stability with a long-term stable macrostructure. Well, this basically means that the doors and the floors do not move around. Also, they assume small-scale dynamics, meaning that the furniture very little over time. In addition, many indoor positioning systems require a floor plan and dense sensing infrastructure, or they use high-end sensors like ultra-wideband and laser to provide accurate positioning. Now, if we make use of the assumptions, we can easily create stable maps, radio and magnetic. We can learn the floor plan. We can adjust our maps, or we can use our really good sensors to provide good positioning results. However, this is not the case with highly dynamic industrial environments like construction sites. In construction sites, we have a combination of indoor and outdoor environments. They exhibit rapid, large-scale changes in structure. There are many moving parts, which makes localization difficult. In addition, workers wear same uniforms, which makes them indistinguishable. Finally, the changing lighting conditions and the many occlusions make positioning techniques very challenging in these environments. And let me show you a few examples. So in this video, we can see the installation of a new wall. You can see that the environment constantly changes, and basically in the next figure, we can see the received signal strength from one access point for a particular worker before and after the installation of the wall. So we are talking about the guy in the circle, and the access point is the green triangle. And as you can see from this graph, the installation of this wall greatly affects the propagation properties of radio signals. Next, construction sites exhibit long-term changes. The environment evolves over time as staircases and entire floors are added. In addition, in construction sites, we have a lot of heavy equipment and vehicles, which makes the use of radio and magnetic maps very challenging. So in this picture, we can see the construction site during our experiments on day one and a few weeks later. And as you can see, the environment changed significantly, and also the radio and magnetic maps changed dramatically. So in construction sites, visual detection of people is also challenging. We have poor visual features in occlusion. We have partial detections and changing lighting conditions, which makes the people detection very difficult. So our aim in this work is to provide accurate and cost-effective positioning services in highly dynamic environments. We also want to be able to identify a particular person using device ID, like a MAC address. And once we achieve these goals, we can accurately allocate personnel and equipment, we can improve productivity, we can identify bottlenecks and provide additional safety, for example, using virtual geofencing. So we can identify danger zones, and we can then notify people to provide better safety. So in this example, we can see that when the goal comes down, we define this as a danger zone, and then we can notify the person that is moving to a safer zone, which is indicated by the green area. These applications are important in construction sites. Okay, so we talked about our objectives. Now we need to figure out what kind of sensors we can use. And luckily in construction sites, we can use a number of different sensors. First, construction sites are equipped with CCTV cameras for security purposes. And in addition, Wi-Fi is also deployed and is used for communication and coordination. Finally, in our system, we assume that IMUs are also available. So we use visual, radio, and inertial sensor modalities. And these sensor modalities are complementary. Visual observations provide accurate positioning, but poor identification, because the workers wear similar uniforms. On the other hand, radio measurements provide accurate positioning, but poor positioning. And finally, inertial measurements provide us, we can use them to have an accurate human motion prediction, but only for a short period of time because of the drift. Okay, so this picture shows a more detailed view of our system architecture. First, we have the input layer, where we use a foreground detector to detect moving people. In addition, we have measurements from radio inertial sensors from multiple people. And now all this data goes as input to a particle filter-based multi-hypothesis tracking framework, which gives us people trajectories indexed by their device ID. Finally, we use the output of our system in order to learn its internal parameters. And this is important because this is what makes our system adaptable to changing conditions. Okay, so let's talk a little bit about state estimation. So the problem here is to track a single target. So we seek to estimate the posterior distribution of the state of a target, which can be the position. So when we know that a particular sequence of measurements originates from the target of interest, we can use the graphical model shown here. So basically, we have the state, the position, and we're going to estimate the state using available observations. So this graphical model is basically the Kalman filter, which we know very well, and we know that it's an optimal MSE estimator. So a different problem now is when the observations to track association is unknown. This problem is called data association. In this case, we need to first find the associations of observation to targets and then do estimation. So basically, the link from the state to the observations here is unknown, and the measurements are anonymous. They don't carry ID. So ideally, we want to model the association of measurement to targets as a variable in our system. And if we consider this, the graphical model becomes like that. So lambda t now is the association indicator and needs to be estimated prior to the state estimation. But we want to use the Kalman filter for the state estimation because we know it is optimal. So what happens to the association indicators? How can we estimate the associations? We can use a particle filter in this case. And the question becomes if this decomposition is possible. So it turns out it is, and you can use something that is called Rao-Blackwellized particle filtering. So basically, we decompose the problem into two parts. First, we have the estimation of data association posterior distribution using particle filtering, and then we can estimate the posterior distribution of target states conditioned on the association analytically using Kalman filtering. So what we achieve is that we reduce the number of variables that need to be sampled, and this is computationally more efficient, especially in high-dimensional state spaces. So in our final model, we use camera, inertial, and radio observations. The camera observations are anonymous, and the inertial and radio ID linked. So the target dynamics are based on inertial observations. The target ID is based on radio observations. We sample only the association distribution, and the state estimation is performed using Kalman filtering. So as I said, we use inertial measurements for the target dynamics, which are embedded in our motion model. So the predicted location is a function of the previous location plus the heading and the step length. Camera and radio measurements are used in the measurement model, so we can predict what are the expected measurements in some location. Okay, so in our particle filter, each particle maintains a bank of Kalman filters, which means that each particle tracks all targets. So in other words, each particle is a realization of the system, which keeps track of the association history. So in each time step, we receive visual, radio, and inertial measurements. So now these measurements go as input to the particle filter, and for each one, we enumerate association events. We basically build an important distribution. We sample from this distribution, and then we update the target with observation. Finally, once we finish with all the measurements, the particle filter can provide us with position and identity estimates. So let me show you an example. Okay, so in this example, color indicates the person identity, the MAC address, and also the dots show the position estimate of each target within each particle. So I would like to note here that occlusion and crossing paths, which happen here, and which is a big problem in visual tracking, are not a problem for our system. When we have occlusions, missing detection, or crossing paths, we can rely on inertial measurements for motion prediction. And basically, we can completely bypass these problems. Okay, so we want a system that can adapt to the changing environment. We can do that using cross-modality training. And the idea is that when the environment is not busy enough, we can use the output of our system, the tracks, as ground truth to train the internal parameters of our system, such as the visual detector, the radio model, the step length, and the maps. To do that, we use a likelihood-based score measure, which quantifies the quality of each track. For example, tracks that have a lot of missing observations, they get a low score. And basically what we want to do is that we want to assess how close is an output trajectory to the actual ground truth. Also, tracks that qualify must exceed a predefined threshold. So, as I have already mentioned, we can use a foreground detector to detect moving people. Okay, so this algorithm basically maintains a statistical representation of the background and can classify each pixel as background or foreground. And there is an important parameter called the learning rate, which controls the adaptability of this algorithm. So one example is when we run the foreground detector using a bad learning rate, this happens here. You can see that we have a lot of noise, we have visual noise, and the people are not getting detected very well. So it's a bad result and we cannot use it. So after tuning, when we find the right learning rate, which happens automatically in our system, you can see that the detection now are more stable, and it's something that we can work with. Okay, so as I said, the learning rate controls the adaptability of the algorithm. A larger learning rate, the foreground detector is adaptive but noisy. A smaller learning rate is slower to adapt but has a lot of misdetection. So we can use the high quality tracks to learn the optimal learning rate. And the idea is that high quality tracks can be used as ground truth. Now, if we try these high quality tracks with different learning rates, the learning rate that gives us the most detection will increase the overall quality score. And in the graph in this graph, we can see that there is a learning rate which minimizes the root mean square error of the output tracks with the actual tracks. And it happens that in that exact location, our metric, our quality score, gets maximized. So basically, we can use this quality score to find the optimal learning rate without needing the ground truth. Additionally, we can learn the radio model parameters. In our system, we are using the log normal path loss model to predict the RSI in a specific location. It's a linear model. It has two parameters. We first initializing these parameters using prior knowledge, taking account the environment. And then from high quality tracks, we can extract the position estimate and radio measurements that are assigned for each position estimate. And basically, we have a data set, and we can perform simple least square regression to refit this model, which happens periodically. Okay, so now let's move to the evaluation. We have conducted experiments in a real construction site in 2 different days. Each experiment was 45 minutes. We used 2 cameras at 30 frames per second. Our cameras were installed on a crane about 80 meters above the ground. We used 12 Wi-Fi access points and 8 BTLE radios. And we sampled the inertial measurements at 100 Hertz from mobile phones. And our goal here is to identify and track 5 specific workers among all other in the scene. Okay, so in our first test, we wanted to study the impact of this cross-modality training. So we start with no training, and we achieve a 90% error of 2.5 meters. So now, as we train the visual detector, and then we go further and train the visual detector and the radio model, and then all together plus the step length, we can see that the error reduces to 0.8 meters, which is significant improvement. So our next test was to study the impact of occlusions. So to do that, we generated artificial occlusions for different settings, and we compare our technique with visually tracking that uses a constant velocity model. So in the first graph, you can see the percentage of occluded FOV for different configurations, and basically you can see that with our technique, we see a significant improvement over the vision-only algorithm. So intuitively, you can see why this is happening using this figure, the second figure, where the gray box is an area, is the occlusion. Basically, it's an area that we don't have visual observations. The red line is the constant velocity model. The blue line is our technique, and the green line is the ground truth. So when we don't have visual observations, the constant velocity model does not know what to do. It can only apply linear prediction, and it keeps the current path using the same heading and speed. In contrast, with the initial measurements, our technique can keep track of the target and it can converge to the ground truth. Next, we want to see the impact of inertial noise. So we inject random heading bias to the heading estimator, and we observed that the proposed technique achieves a sub-meter accuracy for biases up to 30 degrees. So this happens because we can use the camera observations to correct this bias. Finally, we compare the proposed system against RAVEL. RAVEL is a multi-hypothesis tracking system. It's an offline-based approach where possible trajectories are maintained and then Wi-Fi measurements are used in order to find the correct path. So this technique works by considering all frames inside a time window, and the larger this window is, the better the tracking performance. So we compare RAVEL with two settings, time windows of 30 seconds and 6 seconds, and we use this result against the proposed technique, where we compare our technique with a trained radio model, trained radio and visual detector, and trained everything. And basically, we can achieve 50% error reduction versus RAVEL. And the reason for that is basically the cross-modality training and the fact that our technique using the inertial motion model is more robust to occlusions. We don't have crossing paths problems, etc. Okay, so summarizing, the task of tracking people in industrial settings is essential, but very challenging due to the environmental dynamics. We propose a solution that is accurate and cost-effective. In addition, we use the output trajectories to learn different parameters of our system, so we can adapt to real-world conditions. Finally, we run real-world experiments in a construction site. Thank you.